Okay, so today I'm going to talk about the diversity of claystone, and I will talk about this from a geomechanical perspective because I'm not a sedimentologist. I'm an engineering geologist with focus on mechanical and hydromechanical properties of rocks. So first, let's start. Yes, okay. Let's start with the definition of a claystone. So what is a claystone? I think we all agree a claystone is a sedimentary rock, and as the name says, it is rich in clay-sized particles, clay-sized grains. But still, I found it very confusing because in literature there are many classifications and many different schemes how to actually, group claystones, mudstones, shales, and siltstones. So if we take a look here in this list, there are 4 different definitions or classifications, and they all give some different, they distinguish in a different way. So some of them say we have 2/3 of clays, some of them we have more than 50% of silt and clays, and others say we have more than 50% of clay. Generally, claystone is a non-fissile, whereas a shale is a fissile rock. I'll just leave it with this. I do, in this talk, mean with claystones kind of all of these 4 different rock types, because we also have to see that if you are mostly the community of sedimentologists or geologists, talk about a claystone where we have a large portion of clay, whereas engineering geologists or civil engineers sometimes call a shale or a claystone also these these types of rocks here that have higher contents in carbonates and sands, for instance. But what I like is this classification, or it's more a a stream of how actually a sedimentary rock that has started being a soil, then it gets under burial and compaction, and it becomes a claystone. It becomes more fissile, so it gets a shale, and it becomes more like in the end a metamorphic rock. It can also be a argillite. It's in the transition between a shale and a metamorphic rock. And in the end, when we have a lot of temperature and pressure, we end up with slate or phyllite or schist. So why do we care about them, and why do we need to study them? Of course, I don't have to tell you, they are very good for the sedimentary record, for stratigraphy, for paleoenvironment. They preserve fossils, so we can use them for paleontological importance. And they are very important in the resource exploration for oil and gas. But my focus will be on the geoengineering applications. So for underground constructions, transportations, tunnels, mining, dam construction, but also as a geological barrier. So some examples for geological barriers in the construction of dams and foundations, for CO2 sequestration, and for host rocks for nuclear waste disposal. And this is what I'm mainly focusing on. So here we can see an example. This is the opalinous clay host rock. Let me quickly get the pointer. This one, no, it's not. Looking for the pointer. I hope you can see my mouse. So here we can see the host rock with some geotechnical barrier and the canister. I found the pointer. So why is it used as a barrier material? Because it's very low permeable. So usually we are talking about 10 to the power of -12 or even lower. So we're really in the micro to nanodarcy range. It has a very good retention capacity for radionuclides, so it absorbs the radionuclides and holds them in place. And it has a very good self-sealing capability. So if we have fractures in the rock, it is able to self-seal these fractures. If we take a look at a micrograph here from optical microscopy, we can see that we have these very fine-grained clay-rich layers. And if we take a deeper look into it, we can see that these are the clay minerals, and this is basically the matrix, and we have some embedded larger class, so quartz and calcite sometimes. Again, if we could look one resolution down, we can see that these platy aggregates, they form together, and we have different types of water in this system. I will not go into detail now. So we have to really look at the mineralogy and the microstructure, because this is key to all of it. All the good things come with some complications because of the high amount of clay minerals. This is usually very sensitive to drying and swelling because we have the clay minerals here. We can have osmotic swelling and intraparticle swelling. Not going to detail here, but this is a complication because it's really influencing the rock mechanical and also thermomechanical properties. We also have, due to the platy nature and the preferred alignment of all these clay minerals, we have a structural anisotropy. The first part of my talk will be on some clay formations that are used for nuclear waste disposal, and in the second part, I will switch to case studies that we perform currently. So, in a nuclear waste disposal, we usually have here at a certain depth the host rock. This is the example from Switzerland. We have the opalinous clay selected host rock formation, and this is where we build our repository system. So we have a shaft, and we have a tunnel, and we have these repository microtunnels. And what do we need to study now? Actually, to really understand the entire behavior of the host rock, we need to study the thermal, hydraulic, mechanical, and chemical coupled processes. So this is quite complex, it's quite intense because there are a lot of things going on. So we need to understand the thermal behavior. So once we in place the radioactive waste, heat will be produced and the host rock will be heated. So how does the host rock react to increased temperatures of up to 90 or 100 degrees? This is an estimate. What's the hydraulic properties? So what's the hydraulic conductivity? What's the transmissivity? How is the diffusion coefficients? What's the mechanical properties? So when we excavate, when we create these tunnels, how does the material behave? Is it stable? Is it going to form a so-called excavation damage zone around the tunnel? So this is a zone that is characterized by intense fracturing because we unload the material and therefore we increase or we change the stresses and the material becomes, it changes its states. And the chemical reactions. So you see there's a lot of things we need to actually need to know or need to analyze. And according at least to the German Stand AG, which is, I'm not sure how the English translation would be, so the Act for the Site Selection Procedure, the law, it says we need to assess the integrity and performance of the deep geological repository over a lifespan of 100 million years. This is a crazy number, even for geologists. So let's look at some worldwide examples of clay formation that are used for nuclear waste storage. And we can see that actually there is a lot. It mostly concentrates on Northern America, Europe, and Japan. By the way, these are also the countries or the regions where nuclear power plants are used for energy production. Some of them are not active in research anymore, but some are actually quite advanced, for instance, in Switzerland, but I will come to that later. First, let's have a look at Germany. So the site selection procedure has been reinitiated in the last decade, and we have to start over again. And we have to start with a basically blank map, with a white map. And we have to apply, or the BGE has to apply some exclusion criteria, minimum requirements, and geoscientific consideration. So exclusion criteria might be active volcanism, active fault zones, mining industries going on. Minimum requirements would be that we have to go to a certain depth. The host rock has to have a certain thickness. The rock has to have a certain hydraulic conductivity, and so on and so on. And after applying all these different criteria requirements, the BGE came up in 2020 with this map. And as you can see, all three different host rocks are still in the game. So we have clay rock, salt, and crystalline. But now let's focus on the clay rocks. And we have basically two different kinds. We have the tertiary and the pre-tertiary. So we have the Paleogene and the Oligocene. Basically here the molasse in the southern Germany and in the North German basin part. We also have the Paleogene, which is the upper Cretaceous, and the lower Jurassic, which is in this darker purple color. So it is quite a challenge now to really get into all these different clay formations, but we are lucky we can have a look at our neighbors, because our neighbors have been doing a lot of research already on different clay rock formations, and I selected 3 of them that I will introduce quickly now. So let's look at Belgium. Here we have the boom clay. It's not a clay stone, it's rather a clay. Yeah, it's relatively young, roughly 30 million years old. So we are in the Rupelian age. It's deposited in the open marine. And we have the chance to study it in a URL, underground research laboratory at Moel. It's in the northern part of Belgium. And the current depth is around 200 meters. And the maximum burial depth was not really much more. Yeah, it has been maybe 20 meters uplifted, 20 to 30 meters uplift. You can see that they actually constructed the first shaft in the 80s already. So a lot of things have been going on since then. The second one is the Karlovo-Oxfordian argillite. So this is a Jurassic, around roughly 160 million years old, marine, clay stone. They call it argillite. Yeah, it has been brought to higher depths as it is right now. So this is what we call over-consolidated. At Bure, at the underground lab in France, it is roughly 500 meters deep, which you can see here. And some years ago, I had a chance to be there, and you can, it's crazy. There is a lot of things going on, a lot of in situ experiments. There are a lot of tunnels in here, and you really get lost. But it's a really nice chance if you ever have, then just go there. It's really interesting. And last but not least, we have the Opalinus clay. It's also a Jurassic Aeolian age claystone, or sometimes called clay shale. Yeah, it's from a shallow marine depositional environment, and we can study it at the Monterrey URL in Switzerland. It's close to the French border in the western part of Switzerland in the Canton Jura. And the current depth is roughly 200 meters. As you can see here, the lab. We don't have a shaft here because it's next to a motorway tunnel. Yeah, so we can just enter from this side. And they started with the first experiments in the mid-90s, and then excavated some tunnels. And there is also a lot of things going on, a lot of experiments. And Opalinus clay has seen, so in this location, it has been brought up, uplifted. It has seen a maximum burial depth of 1,350 meters, roughly estimated. I'm telling you this because later on, I might talk about the burial effects. So let's look at the mineralogy of these three different clays or clay rocks. They look, on the first perspective, they look quite similar. We do have some larger clasts. Please pay attention to the scale here. So we are really looking at the micro scale. Yeah, these are scanning electron microscopy images. So with optical microscopy, you will be disappointed. So we can see that we actually have some larger clasts here that are embedded in a matrix of clay minerals. Individual clay minerals we cannot see with this method, but you can see them as some fine ground matrix in the background. We do have some quartz in these in all of these rocks here. We have some calcite, which is here and probably here. This is some mica. We have some smaller parts that are here, these very light here components, which are the heavy minerals, so like pyrite or siderite. We also have some carbonate fossil shells, especially here in opalinous clay. And if we take a look at the SE2 images, which gives us basically the morphology of the polished sections, then we can take a look at the pores, and we can see it looks quite the same, but we can see that here the pores, they're more abundant, in the boom clay. And also we do not see all of the pores, but I will leave it now for the next few slides. If we take a closer look at the mineralogy, we can distinguish them in the main components. Of course, they are highly enriched in the clay minerals, above or almost 50%. We do have some quartz, and we have some carbonates, at least in cox and opal. If we take a closer look at the clay mineralogy, we do have some coarse illite smectite, and in the boom clay, we have pure smectite. This is also very important because smectite is the clay mineral that has the highest tendency to swelling. So let's take a look back again to porosity. So here we can see that the boom clay has the highest porosity, whereas with almost like 35 to 38%, whereas cox and opal, they have roughly 15 to 18% of porosity. You can also see that these are not points but bars, because it is actually not really trivial to estimate or to determine the porosity, because it's actually dependent on the method. If we take sorption measurements or optical methods for opalinous clay here, we can see that the pore radius, so to the left, the pore radius decreases, and we have a higher fraction in the very, very small pores. And this is also the complication if we go with optical methods like SEM or FIP nanotomography, which is a similar method, kind of. We are somehow here, we have to stop, because this is just because the resolution of these images is not high enough to capture all these very, very nanometer-sized pores. So this is why we have to go for some other porosity measurements. A good thing is that we can, with these FIP nanotomography measurements, we can create some pore volumetric models. So we can have this volume that can be segmented, and then we can actually see the pore network. So how is the pores distributed? Are they connected? Is there anisotropy? And all these different aspects. If we want to take a deeper look we have to go for TEM, so transmission electron microscopy, here done on opalinous clay. So look at this scale. This is 50 nanometers. Yeah, so we can even see the pores in the clay minerals. But it always comes with a drawback. With TEM, we have to go with very, very small sample sizes. So do we actually have the representative elementary volume, or in this case, representative elementary area? This is a tricky thing. Again, let's look at the comparison of the pore size distribution curves. So we can use the MIPs, so the mercury intrusion porosimetry, and we can see that actually for the boom clay, we have an increase of the amount of pores that have a size of roughly, 10,000 nanometers, so 10 micrometers, whereas we have a increase in the cumulative pores at much, much lower pore sizes. So we have here, let's say, 20 or 30 nanometers. The same is for the COX. So this is just flipped. So to the left side, to the right side, we are getting to the smaller pores, and it's basically similar as we've seen it in the OPA. But we can also see that here in this red and blue color, we have different facies. So depending on where we are exactly, so if it's a clay layer, or if it's a sandy layer, or even a carbonate layer, it really depends and influences the porosity. So if we take a look at the shaly facies of opalinous clay and the sandy facies, we can see that the porosity is fairly similar, I would say. Yeah, this is extrapolated because this is the resolution limit of the SEM segmented pores, and this is just the extrapolation. But if we now take a look at the sandy facies, and the sandy facies also has a sand layer and a carbonate layer, we can see there is actually a huge difference between these between these porosities and pore size distribution, even though we call it opalinous clay. Yeah. Okay, so now I've talked a lot about the microstructure, the pore space and the pore size distribution, but now what's all of this? An important index parameter for us in engineering geology is UCS. It is a uniaxial compressive strength. So you load your sample in axial direction, you have no confinement, and you load it until it fails. And if we now compare the UCS of the boom clay, the Karlovo-Oxfordian and opalinous clay, we can see boom clay is really, really soft. It has only 2 MPa. Actually, it's not really a rock. It's really like a soil. Yeah, you can almost squeeze it with your hands. And the opalinous clay and COX, we have seen that the porosity is fairly similar. The mineralogy is also almost similar, but the appearance of the carbonate is different. So in COX, it serves more as a cementing agent in the clay matrix, and the clay matrix with the embedded larger clast. So this is good because this is increasing the strength of the rock. In opalinous clay, on the other hand, there are these porous fossil shells that I've shown you, and which you can also see in this picture. And they contribute to a large portion to the carbonate content. And these, as you can see, also in the SE2 image here, they have a lot of pores, yeah? And these are really soft and the weakness points. So this is how we can explain actually the difference between the strength of the rock. We also need to look at the microscale when we talk about failure. If we go to triaxial stress conditions, so we have our sample that is confined with sigma 3, that is usually kept constant, and then we compress it until we have shear failure. If you take the sample then and cut it, you usually have these shear fractures sometimes shear zones. It's always scale dependent. And if you take a closer look at the failure and the microscale damage, then you see that it's actually controlled by the mineralogy. So depending on if you have a more competent grain like calcite, quartz, you see brittle fractures. But if you have more a soft material, like these fossil shells or the clay aggregates or these pyrite aggregates, of course, the pyrite itself is super strong, but the aggregate itself is rather soft. You can see more ductile deformation type. So we have some shearing without fractures. It's more like a stretching and deformation. Now let's compare Opalinus and boom clay, and I selected 2 tests that have been done on these rocks at very similar experimental boundary conditions. So we have effective confining stresses of 2.3 and 2.5 MPa respectively. They're fully saturated, and the actual compression, as you can see, that was performed parallel to the bedding direction. And if we now compare the shear zones on the microscale, we can see that here in Opalinus clay, we have a disrupted material. So the fabric is not as it was before. We have some sharp shear zone boundaries. We have some kinking in here. Whereas for the boom clay, it's rather a transition. So the author here has drawn this yellow line, but I think it's more like it's not really a sharp line. It's more like a transition, yeah? We can see that these particles, they have rotated, but they don't look that much different from, let's call it the undeformed host rock part in here. What is, however, different is the porosity. So in OPA, the porosity has increased in the shear zone, but for boom clay, it has decreased. Yeah, so this is very important for the nuclear waste repository, because if we create, due to the excavation, stress changes that lead to failure of the material, and we create shear zones, these parts in Opalinus clay, they would be more conductive because we have an increased porosity. In boom clay, however, we would assume that because of this compactive shear zone, we have a reduction in permeability or hydraulic conductivity. Okay, now I would like to quickly go through some case studies that we've performed. One is the correlation study. So we wanted to know what's actually the, like I already showed you, we have within the Opalinus clay, we have different facies. So what's actually the influence of these mineralogical changes on the uniaxial compressive strength? And therefore we went to the Monterrey underground lab, and we went to this location here because, as you can see, these different colors, they are associated to the different facies. So we have the sandy facies, we have the carbonate-rich facies, and the shaly, carbonate, and sandy facies. So we have this niche, and this is the bedding indicated by these dashed orange lines. And we have some mapping with these subfacies, yeah, from A to D based on mineralogy. And then we performed the UCS tests. So we load the specimen from axial direction and we measure the deformation in axial and radial direction. And from this, we usually get the so-called stress strain curves. So we can see, okay, what's the maximum stress the rock is it's able to withstand. UCS, and we can get some elastic properties. So the most common one is the Young's modulus. It just relates the actual change in height to the stress applied. Then we performed a statistical analysis. So we have grouped the main mineral constituents according to the hardness, and we have 2 petrophysical properties, so the porosity and the density, and then we related to the UCS and the Young's module, which is here, E. We came up with these correlation, and as you can see in the different colors, of course, we have these different subfacies that give us some different mineral contents. But also we can see that these correlate more or less well with the mechanical properties, so with Young's modulus and UCS. But it is now the question, if the porosity changes with UCS, are porosity changes only, or are they also related to the clay mineral content and, for instance, the carbonate content? Because we have seen that actually the layers with clay, they have a different porosity as the layers with carbonate. So therefore, we have to get rid of all the different influences and only focus on one thing. And this is why we have to look at porosity changes with burial depth. So what usually happens if we have the sedimentation of the particles, it's been buried, it will be compacted, there is lithification and diagenesis, and then after all we have this rock. And during this, it loses porosity. As we can see here, we have a rapid change in porosity with depth from, let's say, I don't know, 500 to 800, 1000 meter. It becomes really, really strongly changes. So this is why we have the project called Maturity. So this is on the influence of thermal maturity on the rock properties. First, what we need is a homogeneous facies in the clay formation. And this is the Pliensbachian H. This is the Amaltheen clay. And we need, of course, a changing thermal maturity. And luckily, we found this in Lower Saxony. So we are south of Hanover. And we can see that the thermal maturity is increasing from the southeast to the northwest, because there have been in the past, there have been a lot of studies already in this area. So we are here in the hills area, hills and Sachs syncline. And based on these, we could select the area for our new study. We also have to have a target horizon that is deep enough. We said, okay, we want to be at least 30 meters deep to exclude the weathering zone. We also have to have comparable sections using a marker horizon. And this is just quite good in this area, because on top of these Pliensbachian is the Posidonia shale. And the Posidonia shale, it's quite easy to recognize in the field. It's very dark. It has this smell because it has a lot of organic components in it, and is very, very well documented in the literature. So there has been a lot of things going on in the past. So what we did, we drilled in red, here indicated, we drilled at 5 different locations. We drilled 8 boreholes. We did borehole logging. We did in situ hydraulic testing, both short term and also in the long term, because we installed packer systems that stay permanent at this position. So we can, even for the next years, we can go there and test the hydraulic properties of the rock mass. And we have cored, so we have 500 meters, of course, in Aachen, and we do petrophysical measurements and hydromechanical testings. And all of these results and all of this data should then be compared to the thermal maturity. But how do we get the thermal maturity? We can take the vitrinite reflectance as an indicator for thermal maturity. So these organic rich components on the microscope, and relate them to the maximum temperature that they have seen. And this, in the end, the maximum temperature is an indicator for the burial depth. A second method, it's more qualitative. We can do the rocky wall pyrolysis and have the Tmax, which is not the T burial. I have to tell you this. And it correlates quite well. So the vitrinite reflectance and the maximum temperature from the rocky wall. So if we now take a look at the burial depths, here this is based on the old drillings that have been done in the 90s, because the current investigations are not done, not finished yet. But we can see that we actually have a huge range of thermal material or burial depth from 1,300 meters to, in the northwest, we have more than 3,500 meters. So take a look at the logs. We do have our marker horizon in here, this grayish one. These red and black dots here is the organic and inorganic carbon. Yeah, so the Posidonia shale is really enriched in these ones, so we can have a good, we are certain about the Pliensbachium, which is just below in here. And we can see from the natural and spectral gamma logs that we are really homogeneous. Yeah, so the clay is really throughout the entire depth of the boreholes, it doesn't really change that much, the clay content. If we take a closer look at the mineralogy by the XRD measurements that we've performed yet, we can see that it's high in clay. Yeah, as you can see here, it has some silicates and some carbonates, but we also do see that we have these outliers in here, yeah, where we have a large portion of carbonates, and also the accessory minerals, they increase in these ones here. And this is just due to the siderite concretions that we have. These can be up to a few centimeters, as you can see here, and we have to be very careful when we do our testings, when we prepare our samples, that we do not include these minerals, because they have, of course, a huge impact on the petrophysical and mechanical properties. So let's look at the petrophysics by comparing the porosity of BO2, which is in here, and BO4, which is here, this drilling. So here we are in between 1,000, I would say 1,350 meters burial depth, and here we have 2,650 meters. And we can see, due to the burial depth, the porosity is decreased, because here we have roughly 15%, and here we have 9 to 10%. Let's also take a look at the mechanical properties, but before, I have to tell you that the mechanical properties, it's highly influenced by the water content of the sample. So what we do in the lab, we take the samples and we saturate them to a specific degree of saturation. And this is the way we do it. We place the samples in containers, in boxes that have a supersaturated salt solution that just yields a very specific theoretical relative humidity. And this again is creating a suction pressure. And now I can show you actually the UCS values independence of the suction. You can see again here for the BO2 and the BO4 that I just showed you. And it's really, it's a really good result here that we actually have 2 times higher UCS values for the location that has been brought to what I think it was 1,000 meter difference. This is a really, really good correlation. So not only the UCS, but also the elastic properties. So the higher the burial depth was, the stiffer the material is. So then the last slide, quickly, we have also done hydromechanical tests in consolidated undrained triaxial tests. I will not go into detail here, but you can see again BO2 and BO4. We have a huge difference in strength. So this is when the material fails. So we compress it and it fails eventually. I also plotted the opalinous clay of Monterrey under the same experimental conditions, boundary conditions, and it's just in between. It's and the most astonishing thing is that if we look at the poromechanical behavior, I will not go into detail here now, But you can see the effective stress path, it's really, really similar. Yeah, it's just like a scaling factor. And this is a really good thing, because once we know what the rock has been buried, and what depth it has seen, we can correlate this to the geomechanical, rock mechanical behavior. It seems, for now, it is a scaling factor. And yeah, with this, I would like to conclude. Yeah, for the proper assessment of clay formations, we need, I hope that's all now quite obvious, we need the mineralogy and the microstructure, because we need to study the constituents, the petrographic analysis, grain sizes, pore sizes, and the structural anisotropies, and many, many more things. And in the end, with this, we can estimate or characterize the thermo-hydromechanical and chemical behavior of claystones, shales, mudstones, mud rocks, argillites, or whatever you want to call them. And with this, I would like to thank you, and I'm open for any questions.